want to start with the graph of y is equal to sine of theta. On this slide, we're going to work through getting a table of values for y equals to sine of theta, and then we'll use our table of values to plot the sine function. Let's use the following values of theta to create a table of values for y equals to sine of theta. So I'm going to begin at the value of theta is equal to 0. So for this portion, we're going to get a rough idea of what these values are by using our calculator. First, sine of 0, when we put that into our calculator, is going to give us a value of 0. Next, we're going to input 45 degrees into our value of theta, and if we evaluate sine of 45 degrees, we should get about 0.7. Next, we want to do sine of 90 degrees, and that's going to give us a value of 1. 3 pi by 4 is 135 degrees, and when we evaluate that, we're also going to get about 0.7 on our calculator. Next up is 180, and if we evaluate sine of 180, we're going to get a value of 0. 5 pi by 4 is 225 degrees, and if we evaluate sine of 225 degrees, we should get about negative 0.7 using our calculator. Next up is 270 degrees, that's 3 pi by 2, and evaluating that on our calculator, we get negative 1. Next up is 7 pi by 4, which is 315 degrees, and if we evaluate sine of 315, once again we get a value that's close to negative 0.7. And then finally, 2 pi is 360 degrees, and if we evaluate sine of 360, we get a value of 0. Now each of these pairings here in our columns give us a particular ordered pair on the graph of y equals sine of theta. So I'm going to go ahead and plot those points in blue. Our first ordered pair is at the origin, 0, 0. And then at pi by 4, we have roughly 0.7, so that's a little bit underneath the value of 1. And then at pi by 2, we have a value of positive 1. At 3 pi by 4, it dips down again to pretty close to 1. At pi, we have a value of 0. At 5 pi by 4, we dip down underneath the theta axis, and we get a value that's pretty close to negative 1. Then at 3 pi by 2, we do get negative 1. At 7 pi by 4, we raise up a little bit back to negative 0.7. And then finally, at 2 pi, we have a value of 0. And if we connect these to the best of our abilities with a nice curved line, we get the sine function. I quickly want to give you an alternate way to think about the creation of the sine graph using the unit circle. In this case, the creation of the sine graph depends upon the idea that if we're looking at a terminal point on our unit circle, then sine is going to be the y value or the y coordinate of that terminal point. So let's begin here at an angle of 0. The terminal point here is 1, 0. So that means sine begins at 0. That's the y coordinate of this terminal point. Next, as we begin to move along our unit circle towards pi by 2, our y value slowly increases until we hit our maximum value, which is 1. So here at this point, we have a coordinate or terminal point of 0, 1. Our y value is 1. So let's plot that in. As we move towards pi by 2, we get closer to a value of 1. Next, as we move from pi by 2 towards pi, our y value decreases from 1 down to 0. So as we move from pi by 2 down to pi, we decrease down to 0. And we can continue this motion going from 180 to 270. We're going to be going from a y value of 0 to minus 1, and from 270 to 360 going from negative 1 back to 0. So as we go towards 270, we're heading towards a y value of minus 1, and then back up to a y value of 0. And since we can keep going around and around this circle in the same fashion, our sine function actually is going to continue past a value of 2 pi, and it's going to look similar on the right-hand side of 2 pi and on the left-hand side of 0. Next, we want to use the table of values approach to try to get at an idea of what the graph of y equals cosine theta looks like. So let's repeat the process where we have these particular theta values, and we're going to substitute them into cosine of theta, use our calculator to get an approximate decimal for each of these values of theta. Cosine of 0 is equal to 1, cosine of 45 is about 0.7, cosine of 90 is equal to 0, cosine of 135 is about negative 0.7, cosine of 180 is negative 1, cosine of 225 is again going to be about negative 0.7, cosine of 270 is equal to 0, cosine of 315 is about 0.7, and finally cosine of 360 is equal to 1. Regarding each of our columns as an ordered pair, we're going to get the following. Cosine begins at the ordered pair 0, 1. And then when we get to pi by 4, we're a little bit under 1 at about 0.7. When we get to pi by 2, we're at the y value of 0. At 3 pi by 4, we're pretty close to negative 1. We are exactly at negative 1 when we have theta equals to pi. Then we're going to increase to about negative 0.7. 3 pi by 2, we're going to be at 0. At 7 pi by 4, we're back up to about 0.7. And finally, we end off at 2 pi, where cosine of 2 pi is equal to 1. And connecting all of these points together with a nice curved line gives us an idea of what the cosine function looks like. Next, let's use the ideas from the unit circle to create the cosine function in a different way than the last slide. We're going to begin again here at an angle of 0 radians. And at this particular point, we're going to be looking for our x value because the cosine deals with the x value of any of our terminal points. Here, the x value is 1. This means cosine is going to begin at the point 0, 1. Notice as we move along our unit circle towards pi by 2, our x value is actually decreasing from 1 to 0. So we move along and we have a curved line something like this. As we move from pi by 2 to pi, our x value is going to decrease until we eventually get negative 1 as our x value. Next, as we move from pi to 3 pi by 2, we are increasing back to 0. And finally, as we move from 3 pi by 2 to 2 pi, we increase up to the value of 1. Because we could keep going around our circle in a similar fashion, the graph that we've plotted here is going to repeat itself over on the right-hand side and the left-hand side, like so. On our last two slides, we're going to try to develop the graph of y equals tan of theta. So once again, pull out your calculator and let's evaluate tan at some particular numbers to get a sense of what it might look like. First, let's start with tan of 0. If we input this into our calculator, we should get a value of 0. Next up, we want to evaluate tan of 45 degrees, which should give us a value of 1. Next, we want to evaluate tan of 90 degrees. What you're going to find is, if you're using your calculator, it's probably going to give you an error, or it might say invalid input. So I'm just going to put an x here because we're not allowed to input the value of 90 degrees into the tangent function. Next, tan of 135 is going to give us negative 1. Tan of 180 should give us a value of 0. tan of 225 should give us a value of positive 1. When we try tan of 270 degrees, we're going to get another error. This tells us that the tangent function is undefined at the value of 270 degrees. Next up is 315, where we should get a value of negative 1. And then finally, tan of 360 degrees is equal to 0. The first thing I'm going to deal with are these values that we're not allowed to put as input into our tangent function. Those are going to create two vertical asymptotes, one at pi by 2 and the other at 3 pi by 2. Now in blue, I'm going to go ahead and plot ordered pairs using the columns that we have from our table of values. Our first point is at 0, 0. And then at pi by 4, we have a value of 1. At 3 pi by 4, we have a value of negative 1. At pi, it's 0. And at 5 pi by 4 is positive 1. At 7 pi by 4, it's negative 1. And at 2 pi, it is 0. Now remember, as we get closer to a vertical asymptote, what's going to happen is our y values are going to increase very drastically. So we get an action that looks kind of like this. As we get closer to these asymptotes, the tangent function is going to kind of swoop upwards or downwards like so. Let's now discuss the graph of tangent of x, thinking about the unit circle. Remember that tan of x is the ratio of the y-coordinate divided by the x-coordinate of the terminal point of our unit circle. Since tangent is a fraction, whenever the x-coordinate is equal to 0, this is going to cause a vertical asymptote. And we saw on the last slide that that happens at pi by 2 as well as 3 pi by 2. Those are our two values on the unit circle where the x-coordinate is 0, and that means we're going to have vertical asymptotes on our graph y equals tan of x. Next, let's try to determine where our tangent is identically equal to 0. Tangent is going to be identically equal to 0 when the y-coordinate is 0. And there are two places on our unit circle where the y-coordinate is 0. First at 0 degrees, then at 180 degrees, and then again at 360 degrees. So 0, pi, 2 pi, and so on and so on. Now let's see what happens as we move from 0 radians up to pi by 2 radians. Since the value of x is getting smaller and smaller, this overall fraction is getting huge. So what's going to happen as we start moving towards our vertical asymptote of pi by 2 is that our tangent function shoots up like this. This ratio becomes really, really big because the denominator is very, very small. And this same action occurs as we move from pi towards 3 pi by 2. Since both our x and y coordinate are negative here, tangent overall is positive, but what's happening is our denominator is getting so small as we get closer and closer to y, this overall fraction is getting huge. So we have this action happening again as we approach 3 pi by 2 on the left-hand side. Well, what happens as we approach pi by 2 in this direction? Well, as we move from pi towards pi by 2, notice here that our x values are going to be negative, but our y values are positive, which means that our overall tangent is going to be negative. And as I move towards pi by 2 this way, again my denominator is getting very, very small, so this is going to blow up and tend towards minus infinity. So we get something that looks like this on the right-hand side of our vertical asymptote pi over 2. The same thing happens over here as we approach 3 pi by 2 from the right-hand side. And what happens is tangent is what we call pi periodic. That means that it repeats every pi radians. So we're going to get an overall picture that looks something like this. All right, my little epsilons, stay positive.